So the tower for the power distribution would look something like that. Is it the same in the same in Malaysia? So, yeah. Okay. If you count, I was going to say you can probably just about see one here as well. It's not very clear, but there's 1, 2, 3, 4, 5, 6. So basically, you can have, in terms of selections, 1, 2, 3, 1, 2, 3. So you can build them there. But normally at the top here is the neutral. Okay. They use a much thinner wire, basically at the top, which will be the neutral wire. The others contain basically the three lines. So that's the arrangement. So if we look at basically a typical line, we'll have the generator, we'll have 3 lines, and then we'll have a neutral as well. So as I say, the neutral tends to go on the top. This is obviously 2 lots of 3. Okay, but I think in convention it's probably L1, L2, L3. Okay. And that's, as I say, sometimes you'll get them just on one side of the tower. Okay, so have you seen that before? Something like that before? Okay, is that new to you? Okay. All right, but as I say, this is just showing a generator generating the 3 phases. And this actual diagram is what we would call a star or a Y connection, because as I say, it looks like a Y. Okay, and this again is a star connection or Y connection at the low. Okay, any questions? Does that seem reasonable so far? That's good. Excellent. Right. Good. Move on. Okay, now the title mentions star and delta connections. Okay, now depending on the application of the power, sometimes star is more appropriate, sometimes delta is more appropriate. Can you see the difference now on the loads on the right hand side compared to the previous slide? Again, I'll go back to the previous slide just to show you. Okay, so that's the star. And that's the delta connection. Okay. Now, what we say is that when we're generating our power, we don't tend to use the delta arrangement. Okay? It's not desirable for generators because there is no earthing point, and also third harmonic currents flowing the closed delta causing power loss in the generator. Okay? So you will tend to find that generators will be a star arrangement or a Y arrangement. That's slightly different for the load, but that's basically, as I say, how they're connected together. So I just want to, as I say, conclude for this part of the talk. If the 3 loads on our 3-phase system have the same impedance, the return current to the neutral is 0. Okay, so there's no current flowing at all. In a 3-phase system, the neutral wire is unnecessary only if the system is perfectly balanced. The ideal is to have it balanced. In practice, it's not the case. Okay? Remembering you're balancing the capacitance and the inductance. Okay. Now, if you think about ways that can be achieved, it's balancing out the inductance and capacitance. So it's basically, you can find that if you're generating the power using maybe using some induction, you then have to, induction motors, you then may have to have some capacitor banks to balance the load. Okay, so that's how it can be done. Okay, but what I've said is that we have to take account of if it's slightly out of balance, so that's why we'll have a neutral wire. 3-phase load can either be star or delta, and for a generator, the star connection is the best arrangement. Okay, because it's more efficient. And it avoids harmonics. Okay, so that's, as I say, the basic introduction. Now we shall go on to have more maths. Is that okay? Yeah. I'm sure. Right, okay, so I'm going to talk a little bit now about star and delta connections and the relationship between them. Okay? So, what I'd like to achieve by the end of, in the next sort of 20 minutes or so, I'll describe the star and delta connections in generators, transformers and loads. understanding the relationship between line and phase quantities in star and delta connections, and I'll draw some phasor diagrams. My first phasor diagram, I suppose, was the one on the right. You'll be seeing a few more of those. Okay? But again, it's adopting a similar principle to that. And then what I'll do at the end, quite useful, is to convert a delta load to an equivalent star load. And also vice versa. Okay, so from one to the other, or back. Okay, so on we go. Right, okay. So this is an example of a balanced star connection. Okay, you've got, and it's drawn quite nicely, so you've got the nice thin neutral here, and then you've got the other three, the other three phase lines. Okay, and you've got your VC, your VA, and VB voltages being generated. Okay, so basically we've got our current in the three, which is called I, basically I at 0 degrees. And then we have the line current. Okay, so we're going to have three line currents in basically A, B, and C. So we've also then got the line voltage. Okay, there's a line voltage. So we've got a line voltage between A and B, and we've got a line voltage between A and C. And for a star connection, that's basically the ones that the way that we tend to find it. As you see, there is no none between B and C. So just to define all those parameters in a balanced star connection, so your V0 is basically your phase voltage, which is line to neutral. I0 is phase current. VL is line voltage, which is line to line. Okay, so there's a difference between line to neutral and line to another line. Okay, certainly in terms of the voltage, but also the current as well, depending on the system. Now, because the Malaysian distribution system, or sort of the low voltage distribution system, is similar to the UK, how many volts AC do you get out of a power socket in your house? 240. Is it still 240? Ish. Okay. I think in the UK it's sort of come down a little bit, it's probably nearer 230. Okay. Right, okay. The three phase is normally 415, 415. Okay? But of course, you only see one phase, so only one phase comes to your plug. So what you've got is you've got your voltage basically between this point here and the neutral, okay, which is 240, yeah? Okay. Now the line-to-line voltage is different, okay? Now, would you want to guess what that might be? If it's not 240. Okay, we can come back to it.
No, I get he was mentioning about the voltage level.
Right, okay. It's actually, it's 415. The line-to-line voltage is 415. Okay? But the line-to-neutral voltage is 240. Okay. Now I will try and prove that by mathematics. Okay, but that's what we're trying to do. Okay, so what I've said before, the phase voltage of a balanced star connected source have equal magnitudes and 120 degrees phase difference. Yeah? Because that I showed you in the diagram at the beginning. Okay? So there's basically our recognition of VA, VB, and VC. So taking VA as the reference phase of the phase sequence ABC, okay, and it's basically so we can go through, or RYB, is called positive sequence when VA leads VB by 120 degrees and VB leads VC by 120 degrees. So that's one sequence, and we call that the positive sequence. The other sequence, which is basically ACB, okay? There's only two sequences so in this system. So ACB or RBY, so yeah, red, yellow, blue, red, blue, yellow. The phase sequence ACB is called negative sequence. So it's important to know whether it's a positive sequence or a negative sequence. Okay, so if we look at the phasor diagram, so again, referring to, okay, what we said was we've got VA, VB, VC, those volts. So there we have VA, there we have VB, and and there we have VC. Okay? The negative sequence, there we have VA, there we have now VC, and there we have VB. So they don't look too different, do they? Okay, it's all to do with the connection. All right, but as I say, positive sequence and negative sequence for our three-phase. Now, the voltages VAB, VBC, and VCA are called line-to-line voltages, as I showed you in the diagram. Using KVL, Kirchhoff's voltage laws, yeah. And again, here's where I'll rush through this. We can actually use Kirchhoff to actually work out eventually that we'll be able to calculate the line voltage between A and B. Okay? And it comes down to phase difference of 30 degrees. Okay? And the famous √3. When I was a student, my lecturer said, remember √3. If you can't remember anything else about three-phase, √3. And if you work out, if you multiply 240 by √3, has anybody got a calculator? Come on, somebody must have a calculator. Can you multiply 240 by √3? Tell me what you get. 415. Amazing. Yeah. I know you will get 415. So that is where 415 comes from. Or maybe the other way around, that's where 240 comes from. If you start with 415 and divide by √3, you get 240. Okay. And that's how it works. So, proved by Kirchhoff's law. So, I was going to say, so mathematics can be quite useful sometimes. Okay. So similarly, for VBC, we can work out, again, exactly the same. Different phase, obviously different phase, because that's what we would expect, yeah? Okay. So we've got 30 degrees, 90 degrees, and 150 degrees, okay? So it's basically consistent. Before we had sort of 0, 120, 240. These, as I say, these are different. So if we actually put a phasor diagram of our line voltages, okay? So we said that's basically our VAB. So the result, you can see, is actually going to be larger, okay? So this is our 240. This is our basically our 415. Okay, 30 degrees. Okay, we can do the same for VBC. So it goes like so. And for our basically our VCA, so we've got for our three sequences, as you say. So it's a larger voltage with a phase difference. Okay, so 30 is the same. That's 99. So basically it's 30 degrees different for each one. But again, there's still 120, their phase difference is still 120 degrees. So, in a balanced three-phase Y-connected star system with positive sequence sources, the line-to-line voltages are √3 times the phase voltages, and they lead by 30 degrees. Okay. Over the original, as I say, the original values. So, as I say, for the star system, the line voltage is √3 times, basically times the initial voltage, and the current is equivalent. Okay. And the sum of the line voltages is 0. And also the sum of the phase voltages is 0, which we would expect. Okay, so just quickly to look at the line currents. Those were the line voltages. Okay, so if we consider the line currents. So again, using Kirchhoff's law for each phase and neglecting the impedance of the wires, we're assuming it's going to be 0, what we get is basically we get balanced line currents as well. So what we're saying